SwayamPrabha. Digital India. Educated India.
Hello everyone. So let's continue with the scales of turbulent motion module, where today we will focus on the 1D spectra. So in the last class we started to look at spectra after following up on the 2-point correlation. So just to refresh your memory, we started with the velocity spectrum tensor, which is actually a Fourier transform of the 2-point correlation. So that is this Rij which is a function of R, and small r is the spacing, Rij is the 2-point correlation, right? And the velocity spectrum tensor and the 2-point correlation basically form a Fourier transform pair. So the velocity spectrum tensor is phi ij of kappa. Kappa is in bold, so it's a wave number vector with 3 components, kappa 1, kappa 2, and kappa 3. And it's a continuous wave number vector. And you have it as Rij e to the minus I kappa r, where obviously I is a complex number. So this velocity spectrum tensor is, as I used to say, a loaded function because it has multiple information in there, specifically 3 pieces of information. The subscripts I and j in the velocity spectrum tensor give information about the directions of the velocity in physical space, right? The wave number direction, kappa over kappa magnitude, gives the direction in the physical space of the Fourier mode. And the wave number's magnitude determines the length scale. So 2 pi over kappa magnitude L, which is the 2 pi over kappa magnitude, basically gives information about the length scale. So that is the amount of information that is contained in the velocity spectrum tensor. So we will need to simplify it in order to gather something that is meaningful, and that's what we are going to do. So the basis of that is, if you think about the 2-point correlation, it is basically the correlation between the velocity at one point in space to another point in space separated by r, isn't it? So if you take the correlation of one point with itself, then your small r is 0 because there is no spacing, so you are taking the correlation of one point with itself. So you will have Rij of 0, which is basically the Reynolds stresses, Ui Uj average, right? And that essentially is the triple integral of your velocity spectrum tensor over all the wave number vectors. So you basically get a single number by integrating over all the wave number space, integrating the velocity spectrum tensor over all the wave number space. Okay? Now, there's another quantity that we'll need to get to in terms of getting something meaningful. But before that, if you remember, for the dissipation, one way to get the dissipation is 2 nu kappa squared phi ii. Ii means the same component of velocity here. So 2 nu kappa squared phi ii. Now, so that's the dissipation. Now comes for the energy spectrum function. To get the energy spectrum function, you integrate half phi ii over the spherical space. The spherical space, what do I mean by that? So I had drawn this earlier, right? And since it is on a paper, I am drawing it as a circle. But think of a sphere. Why am I considering a sphere? Because the wave number magnitude in wave number space is square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared, which is like the radius of a sphere. So you can consider the wave number space as a sphere, and with the radius being square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. And you are integrating over that sphere. So here, when you want to find out the energy spectrum function, you are finding out the energy in each wave number, meaning in each shell with a radius given by the wave number magnitude kappa equal to square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. So that is what is shown here in the shaded area. So E of kappa is the contribution to the energy spectrum due to the shell, due to this particular shell with thickness d kappa, which has an inner radius kappa and which has an outer radius kappa plus d kappa. That is what is shown here. I hope this is clear, and I had explained it in the previous class. So that is your contribution to the energy spectrum function. If you integrate that energy spectrum function over all the shells, you get your turbulent kinetic energy. And your dissipation is the same thing, 2 nu kappa squared E of kappa d kappa. So from a loaded energy velocity spectrum tensor, we boiled it down to an energy spectrum function which only depends on the shell wave number. And if you integrate that further, you can get the kinetic energy. And if you integrate that in this manner, you will get the dissipation rate. Okay, so that's where we were at in last class. Today, what we are going to do is we are going to be dealing with the 1D spectrum. So let's consider isotropic turbulence. And it is easier to consider these functions in isotropic turbulence just to gain a better understanding. But obviously this applies to other flows as well. So in isotropic turbulence, where there is no variance with respect to reflections or rotations, then that means the variance in each direction is the same. So U1 squared average is equal to U2 squared average is equal to U3 squared average. And in such a scenario, the 1D spectra, which we represented as E11 of kappa 1, this is related to the longitudinal autocorrelation function, just like the spectrum is related to the 2-point correlation. Here we have E11, so it would be autocorrelation, and it is related to the autocorrelation function. So you can determine the 1D spectra from the energy spectrum function, and that is given by this equation here. I'm not going to be dealing with how to derive it, but for now, just look at the 1D spectra being related to the energy spectrum function in this form. So E11 of kappa 1 is this function here, integral of kappa 1 to infinity, E of kappa divided by kappa, 1 minus kappa 1 squared over kappa squared d kappa. So this is now an integral function, right? Now you can use the above formula to solve for E kappa. So you solve for E kappa from E11. And then what you have is E kappa is half kappa cube d over d kappa, as in differential d kappa of 1 over kappa d kappa E11. So here we started by deriving the 1D spectra from the longitudinal autocorrelation function. Why longitudinal? Because the direction 1 is the longitudinal direction. Since it is 1, 1, it is autocorrelation as opposed to 2-point correlation leading to the velocity spectrum tensor. Here we have E11 for a single component. And you can, so the derivation wasn't shown here. E11, you can express it in terms of E kappa, which is the energy spectrum function. This is the 1D spectra. And then from this equation, you solve for E kappa by taking the derivative of the 1D spectra. Now, if you assign kappa 1 to be 0, so with kappa 1 equal to 0, then you can calculate the integral length scale. And we did this earlier. We derived it when we looked at Fourier transforms in time space. There was a way to actually get the integral length scale, like a large length scale from the spectrum function. And how do you do that? You consider the spectrum function at the lowest wave number, which is 0. So that is what we mean by with kappa 1 equal to 0. You plug in kappa 1 equal to 0 and you get E11 of 0, then you can actually calculate the integral length scale. So the integral length scale is actually directly related to the lowest wave number, the energy spectrum at the lowest wave number. Remember, lower wave numbers are associated with large length scales. So the lowest wave number naturally would be associated with the largest length scale, which is your integral length scale. And since we are using the longitudinal spectra, isn't it? Since we are using the longitudinal 1D spectra, we would get the longitudinal integral length scale. So L11 is pi E11 of 0 divided by 2 U1 squared average. Now, similarly, you can get a transverse 1D spectra. So transverse would be normal to the direction of the flow. Longitudinal would be along the direction of the flow. So you would have transverse 1D spectra, which is E22 of kappa 1 and is given by this equation. Again, I'm not going into the derivations of this. Just take it as these equations given to you. So I have it as half of E11 of kappa 1 minus kappa 1 times d kappa 1 E11 of kappa 1, isn't it? Now, if you think about the Kolmogorov's hypothesis, we know that it would be of the power law form. The 1D spectra would be of the power law form. In that sense, E11 of kappa 1 can be written as C1, some constant, multiplied by A, multiplied by kappa 1 to the minus P. A is some kind of normalization factor. For example, it can be U1 squared L11 to the minus 1 minus P. We will actually see what A is. Depending on which regime you are considering in the scale range, A would be different. But we'll come to that later. So let's say there is some normalization factor so that everything matches. But we have this constant multiplied by a normalization factor, and it would depend on the wave number, of course. So it would depend on kappa 1 to some power. So kappa 1 to the minus P. In that case, if your 1D spectra is this one, then your E of kappa is going to be Ca kappa to the minus P, with C being equal to half P times 2 plus P C1. And E22 would be given by C1 prime A times K kappa 1 to the minus P, where C1 dash or C1 prime is half times 1 plus P C1. So all of this, E of K, we get it from here. And E22, we get it from this equation. So let's see how we can get that. So I have my E11 of kappa 1 equal to C1A kappa 1 to the minus P, isn't it? So let me consider dE11 d kappa 1, isn't it? I'll just take a derivative, pretty simple. So I'll have minus C1P A kappa 1 to the minus P minus 1, isn't it? Simple derivative. And let me consider 1 over kappa 1 dE11 d kappa 1. Then what would I get? Since I'm dividing by kappa 1, I would have minus C1PA kappa 1 to the minus P minus 2. Then I take the derivative of that again, dk of 1 over kappa 1, d kappa 1 of 1 over kappa 1 dE11 d kappa 1. Then I take a derivative again, isn't it? So then the negative goes away and I'll have C1, it is C1P times P plus 2 A and kappa 1 to the minus P minus 3, isn't it? Then let's say I multiply by kappa 1 cube d kappa 1. You see where I'm getting this? I am getting this from here, this equation here. I took a derivative, then I divided by 1 kappa, then I took a derivative again, and then I'm multiplying it by kappa cube. Of course, I have to multiply by half as well. So that's what I'm going to do. So I multiply by half kappa 1 cube d kappa 1, and of this expression 1 over kappa 1 dE11 d kappa 1. And then what do I get? I get half C1 P plus 2 and A kappa 1 to the minus P. So now I can just write this as half or actually let me just erase this. I can just write this as C A kappa 1 to the minus P, where C is equal to half C1 P times P plus 2. Isn't it? So that is my function for, and this essentially is E of kappa, energy spectrum function, Ca kappa 1 to the minus P. I hope this is clear. So I just derived, using E11's equation, I derived something for E kappa. Similarly, we can do it for E22. So E22, I'm going to be using this equation, isn't it? So E22 of kappa 1, okay, E22 of kappa 1 is half E11 minus kappa 1 d kappa 1 of E11. So I will have half, here this one is going to be C1A kappa 1 to the minus P minus kappa 1 and d kappa 1 of E11, which I already derived here. Then I will have, this will be a plus, and C1P A kappa 1 to the minus P minus 1, which is going to be half C1A kappa 1 to the minus P plus, this is going to be C1P A kappa 1 to the minus P. So I can factor out a few terms, and what I'll have is half C1A kappa 1 to the minus P and then 1 plus P. So essentially what I have is half C1 1 plus P A kappa 1 to the minus P. I can write this as C1 prime A kappa 1 to the minus P, where C1 prime is half C1 1 plus P. That is exactly what I had here. C1 prime is half 1 plus P C1. And so I have two equations derived here for E11 and E2, sorry, E of K and E22. So what I did was I started from E11, used this equation to get E of K, then used this equation here to get E22. But one of the things to notice is, so I have E11, which is C1A kappa to the minus P. So it is a function of kappa and it is raised to the pth power. Same goes for E of kappa. Same goes for E22. So all have similar variations with wave number magnitude, isn't it? They are raised to the pth power. They follow a power law. Both, all E of K, E11 of K, E22 of K, all follow a kind of power law with P as the power. We haven't determined what P is going to be, but we'll come to that in a bit. A is some kind of normalization factor. Now obviously their constants are slightly different, their normalization factors are slightly different, but essentially they have the same variation with wave number. That's what we are trying to say, and that is what we have derived here. Okay, this is the autocorrelation function variation in grid turbulence. What is shown here are measurements of the longitudinal autocorrelation functions at three different locations. And here what you have is how f of r is actually varying with r over m, where m is the grid size in your grid turbulence. And f of r is that spacing between the 2 points. These different symbols represent the different locations in the grid turbulence and how it evolves with the spacing of R. As expected, we expect the autocorrelation function, the longitudinal autocorrelation function in this case, to actually diminish as R gets larger and larger, and that is why it is actually a decreasing function. Okay, now what is shown here is the comparison of the spectra that we just derived. So we have it for E of k, E11 of kappa 1 and E22 of kappa 1. And what is shown here is how it is evolving with respect to, so those equations are what are plotted here. Now these are actually derived from what is called a model spectra, which we will actually see in the next class. But essentially these are the three different spectra: the energy spectrum function and the 1D spectra, E of k, E11 of kappa 1 and E22 of kappa 1. You will notice that they have similar variations with kappa. There is a minus 5/3 slope here, which we will discuss in more detail in next class. But what is plotted here is E of kappa versus kappa, and that is why you have two x-axis values here, kappa and kappa 1, and E11 is plotted with kappa 1 and E22 is plotted with kappa 1 as well. Okay, and E of kappa is plotted with kappa. So notice the differences. You have a different kind of variation for E of kappa at the low wave numbers, whereas E11 and E22 have higher values. They do indeed have some meaning. So let's make some observations. In the center of the wave number range, all the spectra exhibit a power law behavior. Here you go. This is the center of the wave number range where all the spectra exhibit a power law behavior. They vary as kappa to the minus 5/3. And that is why on a log scale, you are going to have a straight line with a slope of minus 5/3. Because it is raised to kappa to the minus 5/3, on a log scale, it's going to be minus 5/3 as a line. With a linear, as a line, correct. So, consistent with the equations above, E11, E22 and E are in the ratios 1:4/3 is to 55/18. And that comes from the value of, so here, if you think about it, we are talking about the value of C to C1 to C1 dash. This is basically C1 to C1 dash is to C. And if you remember, your C is half C1 P times P over P plus 2. So C1 dash is, so C1 is to C1 dash is to C is equal to C1. Everything is in terms of C1. C1 is to, what is C1 dash? It is half times 1 plus P C1 is to C, which is half times C1 times P plus 2. Isn't it? So if P is 5/3, then this is 4/3 C1. So we have C1 is to 4/3 C1 because half times 1 plus P is 4/3. Half times 1 plus 5/3, 4/3 is to half times P plus 2. So that is 5/3 plus 5/3 times 5/3 plus 2, that is 5/3 times 8/3, which is 25 over 5/3 times 8/3, which is 40 over, so half times P plus 2. So 5/3 times 5/3 plus 3 plus 2. So I have it as, 5 plus 6, 11, 11/3 and 5/3 times 11/3, which is 55 over 9, and half times that Okay, so half times that, I can just write it as 55 over 18. C1. So that is where we get the ratio of 1 is to 4/3 is to 55 over 18. Another point, at high wave number, the spectra decay more rapidly than a power of k. They decay more rapidly. So here, as you can see, they are decaying much more rapidly than a power of k. So at very high wave number. At low wave number, E of k tends to 0 as kappa squared. In contrast, the 1D spectra is maximum at 0 wave number. This means that the 1D spectra contains wave numbers of kappa greater than kappa 1, isn't it? It again illustrates the fact that 1D spectra contains contributions from wave number of kappa which are greater than kappa 1. And at the low wave number, so what we mean to say is this is kappa squared. This variation is kappa squared. And this is again much smaller than kappa to the 1, because it is much steeper, isn't it? So at low wave numbers, the 1D spectra are in the ratio of 2:1, consistent with the ratios of the integral length scales L11 and L22. So what do we mean by that? This right here, they are almost differing by a factor of 2. And that comes from these equations here. Okay, for E11 and E22. So what we have done here is in this class, what we started to look at was the 1D spectra. We got some equations for those, looked at what ratios they are with relative to each other, and we plotted them based on the model spectra. Now I know I haven't dealt with the model spectra yet, but consider the E of k, E11 of kappa 1 and E22 of kappa 1 behaving in this form. And the main point is they have very similar slope, they have a identical slope in the center of the wave number range. So that's the minus 5/3. Then they have they decay much faster at high wave numbers, and at low wave numbers they vary as kappa squared. So I hope this is clear now. So in the next class we will deal with the model spectra and focus more on the E of kappa. Thank you.